Hey, welcome back, everybody. We are very fortunate to have Victor Chernozhukov today, professor of economics at MIT and one of the people who brought machine learning into econometrics very early on. So very excited to have you. Floor is yours.
Thank you very much for inviting me. So my lecture today is in this paper that we did a couple of years ago. We're still working on it and revising, so any feedback is appreciated. The paper is titled Generic Machine Learning Inference on Heterogeneous Treatment Effects in Randomized Experiments. This is joint work with Mert Demirer, Esther Deflo, and Ivan Fernandez-Val. And the setup is as follows. So we're interested in learning about conditional average treatment effects in randomized experiments. So we have this setup where we have potential outcomes, y1 and y0. There are outcomes in the treated state and the control state, like 1 and 0, respectively. We have a vector of baseline covariates. And the main causal functions of interest are the baseline conditional average. So this is the conditional expectation of y naught, given that, and the conditional average treatment effect function, which is the difference in the two conditional expectation, the conditional expectation of the outcome in the treated state and the outcome in the control state. We make the standard assumption, well, for the RCT, right, that the treatment variable is randomly assigned, conditional on Z, with probability of assignment possibly depending on a subvector of stratifying variables, Z1. And we also assume, because we work with the RCT, that the propensity score is known, right? So this is actually the definition of generalized in RCT in Benson Rubin book, right? So we know the propensity score, P of Z. We make the assumption, we make the nice assumption that the propensity score is bounded away from 0 or 1. And of course, it's a standard result in the literature that under such setup, the regression of the observed outcome on treatment and the baseline controls, a non-parametric regression, recovers these structural functions at least in the population, right? So you define the realized outcome y as one of the potential outcomes depending on what the realized treatment was, and then the regression of y on d and z recovers those functions, the baseline response p naught of z and the Kate function s naught of z, right? So this is the classical result, right? So I'm describing the setup right now. Like it's not, I didn't get to the paper yet. So just describing the setup. So we have the observed data on this triple y, z, and d. It's indexed by I, where I runs from 1 to capital N. And we assume that for simplicity that the data are IID copies of the random vector y, z, and d with some probability law p. So here, like once we have this setup, it's natural, it's very appealing to try to use machine learning methods to estimate the Kate function directly. You know, machine learning is a name that is attached to the new relatively new collection of adaptive statistical learning methods, such as random forest, boosted trees, neural networks, penalized regression, and so on. And they've been shown to be like really successful in various tasks, especially like prediction tasks, like image classification, recommendation algorithms. And they tend to be also like in the modern settings, they tend to be much more successful than the classical methods, like classical non-parametric methods, right? So in principle, it is tempting to apply this machine learning methods to try to learn and approximate this Kate function directly, right? So this map from z, little z, the covariate value to s naught of z, that's the Kate function. It's very tempting to use the machine learning methods. But of course, there are some fundamental and practical limitations in doing this. And I'm going to highlight those limitations and as a motivation for the alternative approach that we will pursue, okay? So there's some fundamental impossibility theorems that that exist, and some of these theorems they actually were developed quite a long time ago, like Stone 1982. For example, Stone shows that if the Kate function is smooth with p-bounded derivatives, then once the dimension of the baseline covariate is modestly large, meaning that the dimension is bigger than the log m, then the Stone's results actually imply there's no uniformly consistent machine learning estimator of this Kate function. Okay, so this is actually quite a severe limitation. Basically, like yeah, like I mean, log of n is a pretty small number actually. So that's one limitation. You know, of course, we could say, okay, this the function class of smooth and functions with bounded derivatives is may still be like very large. Maybe something is better possible with some structural assumptions, and indeed, such adaptive possibilities exist under various form of structured sparsity. There are many results in the statistical learning literature that say, well, if we have some kind of approximate sparsity, whether linear or non-linear forms, we can actually get consistency, and we can even get like very reasonably fast rates of convergence for learning the Kate function. Right, so like there's a bunch of results out there on lasso with approximate sparsity, on random forest with approximate sparsity, neural networks with some sparse weight structures. So that's that's good news and maybe that explains some of the empirical success of the algorithms. Maybe the real data is not like the real functions. They're not they don't live in very high dimensional. So they don't live in very complicated sets. Maybe they are indeed approximately sparse. But the point is that we actually don't know. Like the assumption of sparsity is fundamentally not testable. It is testable against certain deviations, but not uniformly well testable. So we always have to use sparsity with caution, or at least with warning, right? Anyway, so consistency is one issue. Another issue is how do we okay, we might be interested in estimating Kate, but we also would like to have some confidence intervals, right, on the object. But another limitation, and it was also pointed out in the classical framework, that the adaptive confidence sets actually don't exist, and this has to do with biases dominating the behavior of adaptive estimators. So it's not, it's not easy to deal with those cases. There were some solutions proposed by the based on the notions of similarity. Basically, you have to restrict the function classes that you work with, and then you have to do some work on bounding, bias bounding or under smoothing. And there are some possibility results like this, but as far as I know, that these types of results are not yet available for like a random forest in high dimensions, or like neural networks in high dimensions, as to the best of my knowledge. Maybe somebody will email me a link saying, oh, this problem has been solved. I'll be happy to find out if this problem has been solved. But so that's like one set of limitation. Another one is like the practical, like the theory practice gap. The real machine learning algorithms in practice, they have many tuning parameters, and real packages that we use, they are produced by a huge engineering effort by machine learning engineers. There's no guarantee that they set the tuning parameters in the right way, or oftentimes the justification for tuning parameters is heuristic and practice-based. Theoretical justification are oftentimes are existence types results, right? So you read the theorems in various papers, and then they will tell you, well, there exists tuning parameter values such that these methods work under some strong assumptions that's going to be hard to verify in practice. So that's another like practical limitation to keep in mind. So with that in mind, I'm highlighting that, well, there are these theory gaps, there are theoretical limitations, practical limitations, and sometimes these limitations are real. And so here's a funny illustration of this existing gaps and impossibilities. So this is like an application of the Witty Bunny widget on that is deep learning based, and it's supposed to figure out your ethnicity based on the uploaded image. So I uploaded my image from Facebook to this widget, and it predicted my ethnicity to be like most likely East African and only 8% British and Irish. And these results, they don't correspond to 23andMe results that I've obtained, based on genetic testing. So they're quite far away from the ground truth, so to speak. So what's happening here is probably, there's some overfitting going on. Probably when they do the image embeddings, they probably and training, they're probably paying too much attention to I don't know, maybe they're overfitting the colors too much, or maybe not paying attention to the shape. Anyway, so I don't know what maybe tuning parameters, maybe some impossibility here going on. But anyway, it's not working, right? And then the question is how can we, respecting these limitations, how can we develop a more agnostic approach towards inference about Kate? So what we will do, we will treat ML tools as providing us with predictor proxies for Kate. And we're not going to assume that these proxies are consistent or unbiased. Okay. And what we will do, we will post-process these ML proxies to perform inference on key features of Kate rather than Kate itself, right? So we're not going to pretend that we're estimating Kate, but we can actually target certain features of Kate, okay? And our approach is going to be generic with respect to the machine learning methods being used. So in principle, it can be used with various black box algorithms, and you'll see, I'll tell you more about this, okay? So to set this up formally, I'm going to say at the outset that we're going to heavily rely on data splitting, random data splitting into the main sample and the auxiliary sample. So our main sample is going to be indexed by M, and the auxiliary sample is going to be indexed by A. So A and M are going to form a random partition of integers 1 through capital N. Using the auxiliary sample A, we will obtain generic machine learning estimates of the baseline and Kate functions. So capital B of Z is going to be the prediction of the ML proxy for the baseline. Capital S function is going to be based on the capital S function is the ML proxy for the Kate function. So this capital B and capital S are proxies for the little b and little s. They could be bad proxies or good proxies, and you will see we will try to post-process these proxies into something better. Part of the analysis is going to be conditional on the auxiliary sample. In this case, we consider these maps as frozen from the point of view of the main sample, and later on we will drop this assumption. All right. So what are our target parameters? So we target and develop valid inference about the key features of Kate and not the Kate itself. Namely, the parameter number 1 is the best linear predictor of Kate using the ML proxy S of Z. The second target parameter is the group average treatment effect, where the groups are induced by sorting the ML proxy S of Z. So you have candidate most affected group, least affected group, and so on. So we'll try to figure out the average treatment effects for those groups. And the final set of parameters is going to be the average characteristics of units in this hypothesized most and least affected groups. So we'll call this classification analysis. Okay, so let's build the best linear predictor of Kate using this ML proxy. The idea is as follows. So we're gonna consider a weighted linear projection of the observed outcome Y on a set of variables x1. So x1 is going to include a constant as well as the baseline score or baseline proxy. The other axis or the other axis here is going to be the residualized treatment, d minus the propensity score, and the final regressor is going to be the interaction of the residualized treatment with the recentered ML proxy, right? And it's going to be a weighted linear projection in the sense that this error here in this regression equation has to be orthogonal to the axis under reweighting. And the reweighting here is like inverse propensity score type reweighting. So it's divided by the propensity score times 1 minus the propensity score, which we know in the RCTs. And if you look carefully at this weighted linear projection, you will realize that all of these variables, x1, residualized treatment, and the interacted residualized treatment, they all are orthogonal to each other with respect to these weights. And from this, you could deduce this result number 1, which says that these projection coefficients in beta 1 and beta 2, they actually recover the best linear predictor of the later, well, the unobserved true Kate function S naught of Z on these ML proxies, right? So this expression here, beta 1 plus beta 2 times the machine learning proxy minus the recentering, it is actually the best linear predictor of the true Kate given the ML proxies. So in particular, this beta 2 parameter, which we can call heterogeneity learning parameter, that parameter is given by the covariance of the true Kate with the ML proxy divided by the variance of the ML proxy. Okay. So it's worth to consider some special cases to just understand what this is saying. If the ML proxy is the perfect proxy for the true Kate function, then of course this beta 2 is just going to be equal to 1. Of course, in general, beta 2 will not be equal to 1. It's going to correct for some noise in this ML proxy. In particular, if the ML proxy is just complete noise, I'll show you an example of that. Then the beta 2 is going to be exactly equal to 0. Okay. Now, if there is no heterogeneity, then the Kate function is constant, and beta 2 will always be will also be equal to 0. So what does this all mean? Well, I guess this means that if we're rejecting the hypothesis that beta 2 is equal to 0, it means that there is both heterogeneity in the treatment effects, in the average treatment effects, and this ML proxy is the relevant predictor of this heterogeneity. Okay, so this is all identification. In practice, we need to estimate things, and estimation is going to be done using the empirical analogs. So we work with the main sample. We will regress the Y's on the axis and the residualized treatment, and then the interaction of the residualized treatment with the recentered ML proxy. And we will set the residual to be orthogonal to the axis as well as to the weight, right? The weight times the regressors. And this is the empirical measure taken with respect to the main sample, empirical expectation taken with respect to the main sample. And here, because, well, the nice thing about this part is that this is like traditional least squares. analysis, and so you can use your favorite clustered standard errors or fixed effects, things like that, right? So this part is nice and straightforward. Okay, so here's how this works in some simulation examples. I'll show you an empirical example towards the end, but here's how it works in the simulation example. So in one example, this is this example over here. The true Kate is just 0, and this the green line is what the random forest produces in this experiment as a prediction of Kate. Okay. So again, what's happening here is that the true function is 0. The random forest is producing this Kate. Looks like there's quite a bit of heterogeneity predicted. The effects the range from -4 to +4. But when you post-process this green estimate into being the best linear predictor of the true Kate, well, you get something much more. You essentially get something super close to 0. Well, in the population is going to be identically close to 0. This black curve is what you get in the population. So you get this blue curve that essentially post-processes the estimate of the Kate to be like super close to 0, right? So this is what this post-processing does. So one could view this the exercise of building BLP as kind of sensibility check, right? Like, let's just you give me a black box algorithm telling me that this somehow gives me like personalized treatment effect predictions. I could just post-process and verify whether it actually gives me that or not, right? And in this case, it doesn't, right? Like this black box algorithm does predictions, but these are all driven by noise essentially, and the post-process is correctly figures this out. There's another example here. In this case, that the Kate function, and this is an example with just one baseline covariate. In this case, the Kate function is linear, and the random forest here is doing a reasonable job at approximating this linear function. And here, so yeah, the random forest estimate is shown by the green curve, and the blue curve is the corrected estimate, and they're not very different in this case. So in this case, the ML proxy is reasonably good, so there's like a smaller correction happening. So this kind of illustrates the points that I've made here via like simulation experiment. Okay, so before I move to like group average treatment effects, I wanted to make a short digression or stop and say, well, there is also a naive strategy that one might think it would work, but it actually doesn't. Indeed, it's like tempting to, and maybe more natural to just regress the y on baseline, the treatment variable, and the treatment variable interacted with the ML proxy S. But this does not give us the BLP of the Kate. It gives us BLP of the conditional expectation of a function of y given z and d, the best linear approximation to that function. But that function is different. Approximating the conditional expectation function of y given z and d is not the same as the best linear approximation to the Kate. Okay. All right. So I move to the second set of target parameters, and these target parameters are the group average treatment effects. So here we're interested in the expected value of the Kate given the group membership GK. So it's an indicator of being in the group. And here we built the groups to explain as much variation in the Kate as possible. So the group indicators are going to be the indicators that S, the ML proxy, belongs to a collection of regions. So in practice, we take the quintile buckets. The first group is going to be the least affected group. The last group is going to be the most affected group. So these are candidate groups. And we're just going to try to infer the expected value of the Kate given the membership in those groups. Okay, so this is a second set of parameters. And these parameters can also be recovered through a weighted projection where we project the observed y on x1, where x1 is x1 is 1 comma b of z. So it's a constant plus the baseline predictor. And the other variables here is the residualized treatment interacted with group indicators. And the projection is going to be weighted, so meaning that this residual here, this residual has to be orthogonal to the W's, which collects all of these variables here, times the capital W times this propensity score weights. Okay, so in population we can run this projection equation and get these gamma parameters. And this the key result here is that the gamma parameter recovers the expected value of the Kate function conditional on being in the group. Okay, so this is kind of another type of post-processing where, in essence, we use the first stage machine learning algorithm to create groups, and then we do the analysis of on the group average treatment effects. Okay, so that's the identification result. And this is how it works in the two examples that I talked about before. So one example, we have Kate function being identically equal to 0. Another example, you have the linear function. So in the first example, the true gate parameters, they of course are all 0, right? So these black dots are all 0. The red dots is what one would get like naively by just sorting in groups and computing the ML predictors, like the averages of the ML predictors of the Kates in those groups. So this is like super naive strategy. With post-processing, and this is like for the not in the population but in finite sample, we get the blue dots, which are a lot closer to the truth than the red dots in most of the cases, right? So this is this post-processing again does the correct job here, and essentially suggests that the effect there's no heterogeneity here. The effect is 0. In the second case, the ML proxy is pretty good. So you see that these red dots here are not far away from the black dots, which are the true group average treatment effects. And but again, here the post-processing generally improves on the naive estimates. Okay, so but again, there is like a smaller correction here than in this other example. Right, so this is how it works in the simulation experiments. The final set of parameters that we work with has to do with classification analysis. So we look at the least affected group and the most affected group. We look at the vector of characteristics of a unit, GY, Z, and then we just compute the expected value of this characteristics for the groups. That gives us delta 1 and delta k. And of course, these delta 1 and delta k, they are directly identified because they are directly observed, right? So this is the final set of parameters that we look at. And now comes the inference part, the statistical inference part. So far, it's been all about identification. What about inference? So here, our theta, in what follows, theta can denote any generic target parameter or functional. So for example, it could be beta 2, the heterogeneity lowering parameter. It could be beta 1 plus beta 2 times the value of the ML proxy minus the recentering. And you could view that as a personalized BLP, personalized best linear predictor of Kate. Another parameter could be gamma K, which is the gate for the group K. It could also be difference in the gate parameters, gamma K minus gamma 1. It can also be a difference in the like average characteristics, right? Like when we're trying to describe like where the treatment works, we can look at the average characteristics of the most and least affected groups and just compare and test whether there's any difference. So these are the inferential targets. And when we do inference, we have to quantify the uncertainty, and there are going to be two sources of uncertainty. One is going to be estimation uncertainty regarding the parameter theta itself, conditional on the data split. But there is also going to be uncertainty induced by the data splitting, right? So the first accounting for the first type of uncertainty seems like straightforward. It's because we're just looking at projection coefficients or OLS coefficients, and the inference on OLS coefficients has been worked out quite a long time ago. So it's more or less standard. But what about two, right? So different data splits could result in different answers. How do we count for that type of uncertainty? So to account for the second type of uncertainty, what we will do, we will rely on many splits and we will aggregate the results. Of course, the question is how, and I'll tell you how we do this aggregation. So how do we formalize this inference? First of all, we realize that our parameters in principle implicitly depend on this auxiliary sample, right? Because the ML proxies, B and S, they do depend on the identity of this auxiliary sample. And also the target parameter is going to depend on the auxiliary sample. So the target parameter is going to be indexed by A. So conditional on the auxiliary sample, this is a fixed parameter, but unconditionally this is a random variable. Okay, and all of our estimators that we presented, they will have the property that under mild assumptions, the OLS estimators theta hat A, conditional on the auxiliary data, they're going to be approximately normally distributed with mean theta A and variance, which is going to be equal to the standard error squared, right? So that's an approximation result. And so conditional on the split, the standard confidence interval, which is the point estimate plus minus critical value times the standard error, will cover theta A with approximate probability 1 minus alpha. Right, so that's a standard result. So nothing non-standard so far. So that's conditional inference. What about unconditional inference? So different partitions, they will induce different target parameters and different estimators with different distributions, right? Okay, so so if we have different target parameters and different estimators, the question is like what to do. So in principle, there have been proposals in the literature that say, well, let's do the single split, but record the random seed so that the results are replicable and so on. But it's still risky because like what if you are unlucky with your what if your random seed has been particularly unlikely or particularly favorable to the results, right? So maybe there's some risk in this, and we want to make sure that there's better accounting for the splitting uncertainty. So we go ahead and do this accounting, right? Of course, like if you work with big, like rather large samples, that probably this target parameter theta A, right? They would vary very little from one split to another. But in more modest samples, the variation could be considerable. Right? So we want to quantify this uncertainty in a way, and this is like where we get into the non-standard territory. And so we have one proposal I would be interested in your opinions, but feel free to like it or dislike it. It's just one idea on how to proceed. Maybe there are other better ideas out there. There's actually a very interesting recent paper by Larry Wasserman on Hulk, the Hulk approach. Haven't dived into the details yet, but looks very interesting. Also kind of makes use of repeated sample splitting, but does a different type of accounting. So our proposed way of accounting for this sample splitting uncertainty is as follows. So we will aggregate different estimates theta hat a's resulting from different random partitions by simply taking the median of all of these estimates. So we do like 100 different partitions, and we will report the median estimate for the functional of interest. And for the confidence intervals, we will compute various different confidence intervals that we get, and we will take the median of the lower confidence band and the median of the upper confidence band. And we will discount the confidence level from 1 minus alpha to 1 minus 2 alpha. And this is the formal result under regularity conditions. The probability that theta sub a is covered by the confidence interval that I've just constructed on the previous slide is going to be bounded below by 1 minus 2 alpha plus a vanishing term. And here the probability is with respect to both the data and the random partition, right? So here, we are trying to cover, we're trying to contain this random parameter for most of realizations of data and most of the random splits. And so the splitting uncertainty here is reflected in discounting the nominal level of the confidence interval from 1 minus alpha to 1 minus 2 alpha. And this might be a surprising result, but this is a consequence of a result that it's kind of derived from another result that was, I think, first noted by Nicholas Mainshausen in a paper that was joined with Peter Bullman and other co-authors. Basically, the observation that the median of uniform variables a bunch of arbitrarily correlated uniform variables is first order stochastically dominated. So first order dominance by 2 times the another uniform variable. So of course the uniform variables, they represent the p-values, right? So different splits, they're going to result in different p-values. So you can use this result to say something about the median p-values and the confidence properties that guarantees, and then you work with this result on the p-values to convert this result into a confidence interval result, and this is what our paper does. Okay, so that's the result, and so we will take now these 3 results and take them to the real data. This data deals with the Morocco microcredit expansion experiment that was reported in the Crepon et al. Paper 2015. It was a randomized experiment in Morocco to measure the impact of microfinance on financial outcomes. There are 162 villages with 5,000 households. These villages are divided into 81 pairs, and then one village gets to be in the treated group, and another one gets to be in the control group. And in the treated villages, a microfinance institution opens branches, and then 3 years later, the outcomes are observed. So that's the setup. And the why here is going to be the financial profit of the household after these 3 years. Of course, D is the indicator of receiving the treatment. indicator of offering of being able to access the microfinance services. The Z here, the covariates, the baseline covariates, they include 22 household characteristics, such as number of household members, number of adults, the previous use of credit, things like that. And like when we do inference, the inference is gonna, it's gonna include the least squares part is gonna include the fixed village effects as well as the clustering at the village level. And we're gonna try out different machine learning methods. So we tried out like elastic net for predicting baseline scores in the gate function. So elastic net, boosting, neural net, random forest. The question is, of course, how do we actually select the best method? And I didn't say, I didn't talk about this result before because I thought it's going to be more pertinent to mention it here. But basically, we have other results in the paper that say you can actually use this output of those regressions that we described to select the best machine learning estimator, like for Kate, because if you look at this measure, lambda measure, which is the heterogeneity loading parameter squared times the variance of the machine learning score, that's going to be proportional to the correlation squared between the true Kate. So this is Kate, and this is our ML proxy. Right. So and so the like selecting the ML method that gives us the highest lambda is equivalent to selecting the ML method that gives us the best ML proxy for Kate. And similar device works also for selecting the best ML tool, like from the point of view of group average treatment effect analysis. Okay. So anyhow, like if we look at just the BLP results, the best performing methods are the random forest, which is like, actually it's not surprising to me. Like I've seen like over and over that random forest, like with minimal tuning or no tuning, just with default parameters, often produces like best or near the best results. And another method is the elastic net, which produces like second best results here. Neural nets don't perform particularly well here, primarily because like the sample size is not 5,000 is not large here. Anyway, so these are the results. So I'm going to focus the discussion then on this elastic net and random forest results. Here are the BLP results of the effect of microfinance on profits. These are the average treatment effects. Beta ones, the point estimates, the confidence interval, and there's a p-value there. There's also heterogeneity loading parameter, beta 2, and these are the estimates, right? So you have 0.24, 0.279. Note that these are quite different from 1, right? So there's quite a bit of correction happening here. So even though we're trying to predict, trying to do good prediction here, that there's quite a bit of correction, post-processing going on here. So these are not like they're substantially different from 1, but they're also substantially different from 0, right? So which means that there's both like heterogeneity, considerable heterogeneity in this case, and also these machine learning tools, they provide relevant predictors of this heterogeneity. Okay. Right. Okay. So next we look at the group average treatment effects. So given these ML proxies, we create the groups, the most affected group, the least affected group, and we look at the average profit. Average profit that results from the intervention, and over here we see that there's like okay, so there's for the most affected group, the point estimate is 10,000 monetary units. The confidence interval varies from 2,000 to 19,000. So these are wide, like the wide confidence interval. And for the least affected group is like, well, I would say the estimate is essentially 0 with like wide confidence band. If we test for the difference in the gate parameters, like the difference is 11,000, and it's statistically, well, it's both economically and statistically significant, right? Similar results are obtained for qualitatively similar results are obtained with random forest, right? So this difference is 14,000, and it's economically and statistically significant, right? So there appears to be heterogeneity here. And the next question will be like, okay, like who are these most affected groups? What are their characteristics? Like, can we describe them, right? Before I do this, I want to mention that the results that are analogous to this table could also be shown graphically. You could have this plot where you have these five quintile groups, 5 of them. Then there is a group average treatment effect, point estimate. And these are the confidence bands that are constructed to be the 90%, and these are simultaneous confidence sets. So that's a kind of a graphical way of presenting results. It could also serve as a way to do like lots of portmanteau tests, like by just looking at the graphs. Of course, if you want more precise testing, if you have specific questions, you go to specific parameters and you do tailor-made inference. Okay, so that's the graphics. So now let's describe the groups, the most affected and least affected groups. So we're doing here classification analysis for microfinance effects. When we look at the results, we see that the most affected groups. So here we're looking at the characteristics such as age, the household head age for the two groups. Also, like whether they have any like borrowing experience for the most affected and least affected groups. And we see that the most affected group tends to be younger households with less borrowing experience. So this opening microfinance institution seems to help younger households with maybe less borrowing experience, or maybe more limited access to other financial resources. Okay, so I'm close to the conclusion. So I think so it's close to the conclusion. And before I conclude, I want to just give some points on the literature. So I want to mention that, this research that we did, it kind of comes out from the previous research that we worked on in bringing in like orthogonalization ideas or partialing out ideas, double selection ideas, all grounded in classical econometrics into like machine learning. This work is also connected to rapidly developing rapidly developing literature on heterogeneous effects. So there's influential work by the Stanford team, Susan Effie, Hido Imbe, Stefan Wager. So in particular, I like this paper on honest causal trees and PNAS. It's completely assumption-free. It does produce group average treatment effects, like very, very interpretable method. But it also like relies only on a single split. So I think the methods that we developed for uncertainty accounting could be useful in that area as well. There is also very influential work by Stefan Wager and Susan Effie on causal and generalized random forest. This work gives the confidence intervals for Kate, but it restricts the dimensionality of the baseline covariates to be small. Okay, so it does not apply in cases where you have many covariates. There's also work by Opescu and Vasilis Serganis on orthogonal forests This work actually tries to analyze like the high-dimensional setup, assuming a form of sparsity. So if you have a low number of covariates that whose effect is well separated away from zero, you can actually get rid of the other covariates in high-dimensional cases, and you could do some sort of inference. But that inference relies on the separation condition. So that's where the assumptions come in. There's work on using sparsity and lasso. So, like for example, one could model out the heterogeneity by taking the interaction of treatment or residualized treatment with a bunch of characteristics, right, or transformations of characteristics. And the technology for this we provided in this Biometrica 2014 paper, which relied on our work on high-dimensional central limit theorems. Basically, you have lots of coefficients, and you do debiasing one by one, and you create the confidence intervals for this. There's been also like interesting work by Hansen, Cosburn, and Misra on targeted undersmoothing. Like I like this idea that it's kind of you could do it. You could use the methodology for inference on Kate, and what you do, you build your model, and then for the target parameter, you add one. You do it one by one. You add one variable, another variable, and you record the changes on the confidence intervals, and then basically you take the union. I hope I'm not describing the paper incorrectly, but anyway, so it's a very interesting idea there. But of course, here the assumptions the assumptions being made, such as sparsity or approximate sparsity, and so these are more restrictive, right? And there's also like some work on partial sparsity, where you say, I'm going to make a sparse deviation away from a dense parametric model. Like, for example, this is what you use in correlated random effects. You could say I have a good model for correlated random effects, a parsimonious model. I'm going to allow for sparse deviation, but it's still like a kind of sparsity based. Anyway, so this literature is rapidly developing, and there's just like every week there's a paper on heterogeneous effects showing up in our archive. Lots of interesting work. If I miss something, I apologize. So let me conclude by saying that, okay, in this paper, what we try to do, we try to propose generic assumption-free strategies to make inference on key features of heterogeneous effects in randomized experiments. The key features include the best linear predictor, the group average treatment effect, and classification analysis, right? The average characteristics of the most and least affected groups. We also perform repeated data splitting to avoid overfitting, and our inference quantifies the uncertainty coming both from the parameter estimation and from data splitting. Well, thank you so much for this opportunity to present here, and I'm happy to take questions if any.
Thanks so much for the presentation. It was very clear, and it was great to see it applied to a real world data set. There's a couple of questions in the chat. I'm just going to start off with some sort of practical questions. And the first would be sort of, what does this mean for sample size, and power calculations? Is this something that requires a really big study? And then the second was about how to show robustness, that you had the two different ML algorithms that you compared. Do you think that helped to show robustness, or more that was to demonstrate the reliability across multiple algorithms? And what would you recommend in terms of applying this in practice?
Yeah, these are great questions. Yeah, so there's clearly loss of power. Like when we do data splitting, we lose the power. But maybe the power loss is not as dramatic, because the standard error scale, like 1/√n, so we like the precision is reduced by, like when we do like half split, the precision is reduced by a factor of 1/√2, not 2. But when we do the sample splitting, we gain we gain something, right? We protect against overfitting, right? We gain certain robustness, so that's on the plus side. So there's there are trade-offs. Regarding the use of multiple ML algorithms, I would say indeed. So we did. Sorry, I'm just we did design these lambda measures to select the best ones, and maybe when there is clearly the best one, then we should use the best one. But it probably is a good idea to maybe use the best one and the second best one and just see how robust the conclusions are. And then they are roughly similar with both methods. Of course, you could, so they are roughly similar here. They are roughly similar here as well. And what else? But they are different. For the classification analysis, they are different. Like, for example, if I look at the elastic net result here, that there's difference in household age. Well, it's statistically important. For the random forest actually suggests the same thing, also like statistically important. But over here, for the borrowed from any source, elastic net suggests that the most affected group, they borrowed less before, and for the random forest, the evidence is not as conclusive. Yeah, they borrowed less, but this difference is small, right? So maybe so in this case, different ML algorithms suggest different things. So maybe I guess this conclusion is more robust than this conclusion. But anyway, so this is what we see. This is my takeaway. Mm-hmm.
That was helpful. I think Jan has a question or two questions. Do you want to unmute and ask your questions?
Yeah, thanks so much. Thanks for the talk. So I had two questions on some of the sample splitting and tuning. So you mentioned loss in power from basically using only half of the data. What would it take here in terms of theory to be able to do that with cross-fitting where I use both halves? Like, would that make sense here? And I mean, I realize it creates problems because it also changes the estimate. So you kind of average over two estimates, but do you have a sense of what it would take? And then second question, you mentioned that you kind of get a nice loss criterion that you can use to select between models. I was wondering whether you could already have used that in the training data set to do model selection there, or maybe model combination, and whether that could actually give you an additional gain.
Yeah, absolutely. So I'll start with the second question because it's closer to the topic, more closer to the, you could. We have a remark in the paper, like maybe a short section in the paper. You could say, well, this is like a post processor. Like I download a high quality package called Random Forest, and I run my algorithms. I do post processing, but I could also step back and say, well, I actually want to train my ML algorithm with the purpose of predicting Kate itself. Then I need to change the loss functions. And in principle, you could use the loss functions based kind of motivated by the strategies that we described. And I talk more about this in a section in the paper, right? So you could, in principle, change your loss functions and train the ML algorithms in this way. And I think the similar proposal was made by Ni and Wager. Like, I think this called something like learning objectives, or I forgot like the exact name of the paper. There, the idea is that you also modify the loss functions like depending on your learning goals, and then you train the ML algorithms in the first place to aim at the object that you want, the Kate, right? So this is a super good point that you're making. yes, you can. You can do this, and also, but still, the inferential tools that you get from our paper, I hope they're still useful for like inferential purposes, right? Regarding the full use of the data, indeed, there is I think if we have some kind of I think if we have like maybe there's it's possible to show something that if we have a consistency. Well, for sure, if we have consistency for Kate itself, like I think, this cross-fitting, like cross-fitting would work. We have this work with Vera Semyonova, where you try to leverage strong assumption and you don't lose any efficiency, so you get no loss of efficiency in this case. There might also be no loss of efficiency where the function, like the ML proxy, is not not consistent for Kate, but across different splits they're consistent for the same quantity. There might be some kind of result for this case, but I don't know, like off the top of my head, if there's such a formal result. There might be. Yeah, it's good to check.
That's super helpful. Thanks a lot.
Thanks.
Sammy, at this point, are there more questions, or should we just break?
No, there's no more in the chat, so I think we can break.
Okay, so Emily, at this point, let's stop the live stream.